Welcome to Introduction to Geology. In this series of modules, we're focusing on the Earth system, geology as a science. In this particular module, we'll discuss Uniformitarianism and Geodesy, study of the Earth's shape and structure. I'm Dr. William Patterson, and I'll be leading you along this excursion. As humans, we observe nature on Earth. As scientists, we observe nature and think about how to mimic that experience in a lab where you don't have other things going on that might influence the results, how you interpret what you observe. As a result, there are many subfields in geology that include oceanography, ecology, geophysics, geochemistry, cosmochemistry, and geobiology. Thus, geology isn't merely looking at rocks. Additional related fields include planetary science, where you might make geological observations that rely on what we call remote sensing. We can use a spectral analysis of light coming from a planet that tells us what's on that planet's surface. Another special aspect of geology is probing the Earth's long history, looking back in time, and also looking forward in time. This is something that only a few other fields examine. Biologists, of course, study evolution, how plants and animals change over time, how they got to where they are, and where we think they may be going. That's similar to geology. In fact, relies on geology for its evidence of the past. Geology really employs the aspect of long time as a prime component of the science. One of the most important principles in geology is the principle of uniformitarianism. The principle of uniformitarianism states that the present is the key to understanding the past. This is generally attributed to Charles Lyell and/or James Hutton, but it's possible that the statement was originally made by William Whewell. This idea that the present is the key to the past implies that you can look at what's going on in the world today and assume that's been going on in the past. Therefore, using what we see today can describe what had happened in the past, and hopefully at some point we would develop some means to determine how far back in the past that thing did happen. Early in geology, we didn't have the ability to tell time in a specific way. As an example, here in Arizona we have two processes, one occurring very slowly and one that occurred very rapidly. When we look at these two images, we're going to see that the rocks at the bottom of the Grand Canyon are about 2 billion years old, and the most recent layer of sediment is about 250 million years old. That means whatever happened here occurred between 250 million years ago and the present. When we look at this excavation near Winslow, Arizona, not very far away, maybe 100 kilometers from the Grand Canyon, we see evidence for an explosive impact of a meteorite that created this crater in a matter of seconds. In this event, the excavation occurred very quickly, whereas the Grand Canyon probably took around 50 to 70 million years to develop. Now we're going to spend some time talking about the Earth's shape and its surface. This is known as Geodesy, the study of the Earth's shape and surface. The ancient Greek scholar Eratosthenes showed us the Earth was spherical, kind of like his head in this image. Modern research, however, shows that the Earth is not a perfect sphere. In fact, the Earth's topography, or surface elevation, ranges from nearly 20 kilometers, from the highest point on Mount Everest to the Mariana Trench, the Challenger Deep, which is around 11,000 meters below the surface of sea level. And we use sea level as a reference for all Earth's surface and seafloor elevations. So everything we do talk about when referring to the surface of the Earth is relative to sea level. Something that we will see later in the course isn't actually a steady feature of the Earth. Sea level rises and falls for a variety of reasons over Earth history. Here we have Mount Everest on a somewhat typical climbing day. This is the highest point on the surface of the Earth today. Conversely, in the Pacific Ocean, we have the Challenger Deep, which is located to the west of the island of Guam. Mount Everest, the highest point on Earth, is 8,849 meters above sea level, whereas the depth of the Challenger Deep is generally accepted to be 10,929 meters. So around 9,000 meters above sea level and 11,000 meters below sea level. That's the variation in the Earth's surface. Over 2,000 years ago, ancient Greek scholar Eratosthenes demonstrated that the Earth was spherical and accurately measured its circumference. In the mid-20th century, we began launching satellites into space that would help us determine the exact circumference of the Earth to be 40,030 kilometers. But over 2,200 years ago, in ancient Greece, a man arrived at nearly the exact same figure by putting a stick in the ground. a Greek mathematician, scientist, and the head of the Great Library of Alexandria. Eratosthenes had heard that in Syene, a city south of Alexandria, that no vertical shadows were cast at noon on the summer solstice, when the sun was directly overhead. He wondered if this was also true in Alexandria. On June 21st, he planted a stick vertically in the ground and waited to see if a shadow would be cast at noon. Yes, it turns out there was a shadow, and it measured about 7 degrees from the vertical. If the sun's rays are coming in at the same angle at the same time of day, and a stick in Alexandria is casting a shadow, while a stick in Syene is not, it must mean that the Earth's surface is curved. Eratosthenes probably already knew that the idea of a spherical Earth was floated by Pythagoras around 5000 BC and validated by Aristotle a couple centuries later. If the Earth really was a sphere, Eratosthenes could use his observations to estimate the circumference of the entire planet. If the difference in shadow length is 7 degrees between Alexandria and Syene, that means the two cities are 7 degrees apart on the Earth's 360-degree surface. Eratosthenes hired a man to pace the distance between the two cities and learned that they were 5,000 stadia apart. This is about 800 kilometers. He could then use simple proportions to find the Earth's circumference. 7.2 degrees is 1/50th of 360 degrees, so 800 kilometers times 50 equals 40,000 kilometers. And just like that, 2,200 years ago, a man determined the circumference of the entire planet with a stick and his brain using the scientific method. When we look down into the Earth, we notice that the Earth appears to consist of layers. Seismic waves that travel through the Earth behave in a way that differs depending on the depth. This change in behavior with depth provides us with an illumination of what's going on inside the Earth. Compression and shear waves behave differently and are going to be bent or absorbed at layer boundaries differentially within the Earth. When the Earth interior transitions from a solid to a liquid, or a solid to an even more dense solid, that's going to change the behavior of these waves as well. The Earth's interior is therefore layered according to density and the physical state of the material, whether it's solid or liquid. Rock density at the surface of the Earth is slightly less than 3.5 grams per centimeter cubed, while whole Earth density is about 5.5 grams per centimeter cubed. We can measure rock density at the surface to get an accurate number for that surface density, and we can use the Earth's gravitational pull with some basic physics to determine the whole Earth density. Now that we know the surface and the whole Earth density, we can calculate the core density that should be about 8 grams per centimeter cubed. Thus, the core is almost 3 times the density of surface rocks and almost twice the density of the whole Earth. The core is significantly more dense than other portions of the Earth. When we look at it schematically, we can see that we have a crust, an outer rigid portion of the Earth. We have a mantle that's mostly plastic, kind of toothpastey, a very thick, very hot toothpaste. Further down, we have a liquid iron outer core, a very dense liquid molten metal. Then we have a solid inner core that's composed principally of iron. Why all the iron near the center of the Earth? Well, early on in Earth's history, as the Earth was getting bashed by planetoids and planetesimals, asteroids, meteors, meteoritic dust, it was pulverized, and this pulverized material was somewhat homogeneous. As this bashing continued, the heating of the Earth continued, and that provided the time and impetus for differentiation, a separation of materials based on density in this case. This differentiation is going to occur gravitationally, so we start out with a bulk Earth with a uniform composition. We begin to develop oceans and atmospheres above the surface of the Earth as it cools. As cooling continues, we proceed with differentiation of the whole Earth into continental ocean crust, depleted mantle, and primitive mantle, with the core remaining relatively isolated. This overturn of materials, the sinking of iron towards the center, and the migration of lighter elements towards the surface is known as the iron catastrophe. Catastrophe means to turn over. It doesn't necessarily mean a disaster, although we use it as a disaster term. As a result, if we send seismic waves through the Earth, we're going to see change in velocity. P waves, primary waves, are going to exhibit an increase in velocity with increasing depth due to density. Then a slight decrease right here where there's partial melting of the upper mantle. Then, as density increases further into the Earth, the P waves are going to increase in velocity until they reach the liquid iron outer core, where they slow considerably. P waves again increase in speed as they go further and further into the core towards the center. S waves, which are secondary waves, behave differently. S waves are shear waves. They're going to show a similar profile until we get to the liquid iron outer core. At this point, because they're shear waves, they don't propagate through a liquid. They go away suddenly. They reappear suddenly in the inner core where P waves are being converted into S waves. So the S waves don't come back. They're just created in a different way at this boundary. When we put these different materials together, the crust is going to be composed of continents made of less dense material. This less dense material literally floats on more dense material. In this case, we have continental crust comprised of carbonate rock and silicates predominantly. That's going to ride on top of oceanic crust, which is principally basalt, a mafic igneous rock. Usually the oceanic crust, being weaker, denser, and thinner than continental crust, will get pushed underneath the crust or get abducted onto the crust. This is all going to float on a mantle which is significantly more dense.